Okay, good morning. It's time for entertainment, right? So it's our great honor actually to start this ICCV2019 with wonderful oral presentations. So my name is Kohn from KAIST, and I'll co-chair with Nikos Paragios together. And we will have 4 papers, as you saw just before. So each paper will have 15 minutes presentation and 3 minutes for Q&A. And for this special session, we will have microphones installed a few places. So after authors' presentations, please come forward to the microphone to ask some questions. Okay, let's welcome the first presentation.
Okay, hello everyone. I'm Anant.
And I'm Atul.
And we are going to talk about single-photon 3D cameras. Let's take a look at this photo. It appears as if a bean-shaped hole has been cut out of it. But this is actually a real picture taken by a camera without any modifications. There is a 3D object in here, which normally looks like this. This is the Chicago bean. Many of you may have seen it. The reason why it looks so different here is because it has been coated with a very dark material called Vanta black that absorbs almost all the light falling on it. And because of that, there is an extremely small amount of light coming back to the camera. And as a result, we cannot identify the object or infer its 3D shape. Here's another example. These images were taken in a dark environment. Once again, if there's not enough light reaching the camera, it is difficult, if not impossible, to perform a computer vision task. Example, in this case, we cannot detect the faces, whereas if the scene were bright, we would have been able to detect all the faces. In general, there are many real-world applications where we need to capture images and perform computer vision in the dark. A conventional camera cannot reliably operate under such low illumination scenarios. If we don't get enough light, we can hardly make an image, let alone perform any high-level computer vision tasks. Now, there do exist these specialized cameras for low-light imaging, like these shown here, but they can only operate under controlled environments. Example, the one on the left needs to be super-cooled to -100 degrees. Moreover, these cameras cost a fortune. And as a result, they cannot be used for everyday consumer-grade computer vision systems. Fortunately, there is this emerging class of extremely sensitive sensors called single-photon sensors. One way to think about a camera pixel is as a bucket that collects photons. For conventional cameras, the bucket needs to collect hundreds to thousands of photons to reliably create an image. In contrast, a single photon pixel can be thought of as a very small bucket, almost a teaspoon, which collects only 1 photon at a time. This makes these extremely sensitive. In addition to their extreme sensitivity, single photon cameras can operate at room temperature. They do not require any special operating conditions. But perhaps more importantly, these are compatible with CMOS manufacturing technology, which is the same technology used in almost all cameras today, ranging from cell phones to machine vision cameras to 3D cameras. This means it should be possible to manufacture single photon cameras at scale at quite low costs. Because of their extreme sensitivity, single photon cameras are driving an imaging revolution, especially in applications like astronomy and ultra-low light microscopy, which are inherently photon-starved, meaning that the camera doesn't receive enough light. But for any real-world computer vision application, a camera needs to work not just in dark, but in all light conditions. But a problem arises when we operate single photon cameras in bright conditions. Remember, a single photon sensor fills up after capturing just 1 photon. This means that in normal to bright conditions, most of the photons will be missed. And it seems that all this information carried by the photons will be lost. Does this mean that single photon cameras are limited to only niche, low light applications? Or can these cameras be used in a broader range of conditions, in particular bright scenes, which is important for computer vision? We are going to address this question in the context of 3D imaging. It turns out that in addition to being sensitive to individual photons, single photon sensors can record the time of arrival of each photon with very high timing resolution. This makes them a natural candidate for 3D imaging using the time of flight principle. A typical time of flight camera has a laser light source which sends out a short light pulse towards the scene. The pulse travels to the scene and comes back. And there is a stopwatch that measures the total time of travel. The camera then estimates the scene depth using this round trip time and the speed of light. The precision of this depth estimate clearly depends on the timing precision of the sensor, which is very high for a single photon camera. So this simple time of flight principle is in fact the workhorse of many commercially available 3D imaging devices like the Kinect or the Velodyne, which many of you might have worked with. Now, it would have been nice if we could simply replace the conventional image sensor in these devices with a single photon sensor. However, a single photon sensor has a very different image formation model. We cannot simply replace it. Let's see how it works. Suppose the scene is illuminated only by the 3D camera's laser source. There is no other light source. For example, there is no sunlight. Since the laser source emits a laser pulse, the light received by the sensor is simply a time-shifted version of the pulse. To the sensor, the waveform looks like a stream of photons. Remember that the sensor can only detect one photon at a time, so it will end up detecting only the first arriving photon. This is an important property, and we'll keep using this. Now, one photon may be noisy, so in practice, we repeat measurements over many laser pulses, each time recording the time of arrival of only the first photon. Using these photon detections, we make a timing histogram, which resembles the shape of the incident waveform. By locating the peak of this histogram, we can easily get the time of flight. And because these sensors are so precise, just a few photon measurements are enough to give these exact depths. So to summarize, a single photon sensor can recover 3D images very accurately in the dark. But like we said before, in order to be practically useful, these sensors need to work not just in the dark, but adapt to a wide range of illumination levels. So let's see what happens when there is sunlight in the scene. The light received by the sensor still has a peak, but now it also has a constant component due to sunlight. And now, in addition to the source photons, there are many more sunlight photons. This causes a problem because these sunlight photons arrive all the time, meaning they can arrive before the source photons. And so the first photon in each photon stream is likely going to be from sunlight. And since we detect only the first photon, this means we hardly ever get to detect the true source photons. This leads to a distorted histogram. The true peak is buried under sunlight, making it hard to locate. Stronger the amount of sunlight, stronger is the distortion, and the harder it is to locate the peak. Here's an example result. The single photon camera can recover exquisite 3D details under no sunlight, as seen on the picture in the left. But even with moderate levels of sunlight, we see large depth errors. This distortion due to sunlight cannot be overcome even by increasing the source laser power, because later arriving source photons will still be masked by early arriving sunlight photons. The current method to deal with sunlight is to block light at the sensor using an absorption filter. By blocking the sunlight photons, we are giving the source photons a better chance of being detected. But now the problem is that the filter blocks source photons as well. Therefore, even though the histogram is no longer distorted, the signal to noise ratio is very low, and we still can't hope to find the peak. Clearly, blocking light is not an ideal solution. So can we do single photon 3D imaging in bright sunlight without blocking any light?
So it turns out that the answer is yes, and let's take a look at how. Our key observation is that the probability of a photon getting detected depends on how far it is from the start of the sensor. In particular, this probability decays exponentially as we move farther out. Now, conventionally, the sensor is turned on at the same time when the laser pulse is transmitted. So the probability of detecting the source photons that would arrive later is very low. So here's an idea. What if we placed the start of the sensor just before the laser pulse? This will give those source photons a chance of being detected. But the problem is we don't know where that peak is. In fact, that is the whole thing we are trying to estimate in the first place. So there is a bit of a chicken and egg problem here. So let's see what we can do. Our main idea is that we are going to hedge our bets, and we will use different sensor start times for different pulses. We will distribute our sensor start times uniformly, and this way we can improve the chances of capturing those source photons in at least some of the pulses. We call this method asynchronous operation. By summing all of these measurements over many pulses, we get a histogram that looks like this, and as we increase the number of shifts, the histogram will start resembling the true waveform shape, free from any sunlight distortion. So our main contribution in this work is that we can average out the effect of sunlight and reliably recover the true source peak even in the presence of bright sunlight. So we can compare this with the conventional acquisition method, and as we can see, the peak in the conventional method is buried in the noise, whereas the peak is easily detected with our asynchronous acquisition. Now, one way to delay the sensor start times would be to make the sensor cycles longer than the laser cycles. However, this is not very time efficient. A better way to achieve asynchronous operation in practice is to let the photons themselves determine the cycle lengths. The key idea here is that because the photons arrive randomly, it automatically forces the sensor cycles to shift. And in the limit, we achieve uniformly shifted start times automatically. Photon-driven acquisition is very easy to implement because we don't need any special synchronization circuits, and in most cases, it can be easily implemented with a simple firmware update. Let's look at some experimental results now. Here's our single pixel raster scanning hardware prototype. For the first experiment, we imaged a scene with a large dynamic range of albedos. This is a challenging scene because the darkest scene points and the brightest scene points are apart by almost an order of magnitude. With the conventional method, we can either recover the dark objects or the bright objects, but with our photon-driven acquisition, we can automatically adapt to this wide range of albedos and recover both of them simultaneously. In our second experiment, we imaged a white porcelain flower vase under bright illumination like sunlight of over 20,000 lux. Once again, our photon-driven acquisition technique provides almost an order of magnitude improvement in depth reconstruction accuracy. This shows that we can now start thinking about using single-photon cameras for 3D imaging outdoors in sunlight. And because they have picosecond timing resolution, they can potentially achieve near laser scan quality at long distances. For long-range 3D imaging, the current state-of-the-art conventional LiDAR technology can provide maybe centimeter resolution at hundreds of meters away. So for example, if you're imaging a person standing very far away, you can maybe make out that there is a blob. But with our work, it may become possible to start seeing finer details and maybe even start recognizing the person using some high-level computer vision algorithms. So to summarize, our work shows that single-photon 3D cameras can be used for obtaining high-resolution depth maps even at long distances while using low powers. In addition to 3D imaging, single-photon cameras also have many other applications in active imaging tasks where sensitivity and resolution are important. For example, fluorescence microscopy and non-line-of-sight imaging. So it can be used in situations where the waveform shape is not simply a shifted pulse. Now, it may seem that single-photon cameras are these esoteric technology, but it turns out that they are becoming commercially available now. This presents an opportunity for the computer vision community to develop new vision algorithms and leverage the unique capabilities of these single-photon sensors. Our work takes some initial steps towards realizing that goal of extreme vision applications using single-photon cameras. Thank you very much for your attention, and we are happy to take questions now.
We have time for a couple of questions. Please approach the microphone if you have a question. Okay.
Could you
just approach the microphone? There is a microphone in front of you. Yes, go ahead.
So now that you are combining information across time, there is an impact on frame rate or the scanning rate. And you probably also need your imaging platform to be stationary, and the thing that you are imaging to be stationary as well. Can you explain more on that?
So if I understand the question correctly, you are saying that for single photon 3D imaging cameras, you need to have more stability of the camera platform. I believe it's the same as for your regular LiDAR cameras. There's no added constraints that are imposed.
And also we are able to show these results with the same acquisition times as a conventional method would. So we are not adding anything in terms of acquisition time. We are just using these extra shifts instead of keeping them all in the same place.
If there is a follow-up question, it has to be short.
But since you are capturing multiple observations to make one measurement, that probably has an impact on frame rate.
So maybe we can discuss the details offline, but it's possible to do this with like real-time scanning. There are commercial single-photon LiDARs that do this at real-time frame rates.
Okay, there is another question on the way to the back.
So have you considered your approach under the non-line-of-sight imaging setting? And if you have, then are there any kind of special considerations that you need to give it?
So we haven't looked at non-line-of-sight imaging in this work, but as we discussed, the active imaging framework is very wide. So you can adapt our techniques to almost any active imaging application, including non-line-of-sight imaging. The optimal acquisition strategy may vary. It may no longer be a simple asynchronous acquisition scheme, but it's possible to think about what the optimal acquisition scheme is going to be.
Thank you.
Okay, it's now, let's thank the speakers and move to the next talk.
So the next talk is titled as Specifying Object Attributes and Relations in Interactive Scene Generations. Authors Oron, Ashual, and Lior will be presented by Oron. Okay. Let's welcome the speaker.
So, good morning, everyone. My name is Oron Ashual, and I'll present a paper I co-authored with Professor Lior about a new way to generate images interactively. So the question that lies in this paper is how can we accurately and efficiently describe an image without using the image itself? Let's assume that we have this, like a user who is thinking about this random image. What is the simplest input we should require in order to generate a similar image to what the user has imagined? So there are a few possible solutions that I guess most of you are probably familiar with. The first thing is we can ask a segmentation mask. This will probably reach the most accurate results. However, we don't all possess this drawing talent. Another option is to input text in natural language. Natural language is very intuitive to users, but when the scene is getting complex, it will probably require a very long description. The last solution we looked at is using bounding boxes. This solution requires the user to accurately draw the dimensions of the elements, which may not be necessary. And again, when the scene is complex, it's getting unwieldy. So understanding the benefits of each of these solutions, we came up with 4 requirements from an input of an image generation tool. So in order to accurately generate the image, we will have to know 4 things. What objects are presented in the image, the relations between the objects, the size and locations of each object, and finally, the appearance of the objects. How do they look like? We assume that reaching the desired image will require multiple tries, so we design an interactive environment, modeling it in a way that changing one attribute will have the smallest possible effect to the rest of the image. And thus, we'll let the user play and make changes until the desired output is reached. So let's focus on the first 2 elements. The relationships between the objects are best captured with a scene graph. We use a scene graph that is similar to that of Johnson et al., where the nodes are the selected objects, kite, sea, fog, sand. And the edges are the relations. Since Coco, the dataset we have used, does not contain annotations of complex relations between the objects, we are using relative positions as the relations, surrounding, above, left of, right of, inside, and below. The location of the objects are defined through a 5x5 grid, which gives us a coarse location, and the size of the object is 1 out of 10 different sizes. For the appearance part, we require a reference appearance image for each object. In the first example, you can see a reference image for the sky object. The output image is changed accordingly. Notice that the image should capture the spirit of the object rather than present the object itself pixel-wise. Since this method requires too much effort, we also offer to choose one of the archetypes from the latent space of the model, as you can see in this example. So our tool is designed to be both easy to use and have the ability to produce diverse images. Here is a short demo of it. In the demo, you can see the different objects in the coarse locations on the grid. The sizes are represented by the font size. We are now adding a new object, a river, and then changing its size. After that, we will move it around the grid to different locations, and then the image will change accordingly. And finally, we are traversing the latent space of the river appearance to produce different images. Okay, so after this long introduction, let's dive into our chosen architecture. And for the example, let's take an image of person skiing. Once the user sets up the desired objects in the user interface, person, snow, skis, etc., we are creating heuristically a scene graph. Each object in the scene graph is a concatenation of 3 vectors. The class learned embedding, 1 not vector in the size of 25 for the coarse location, and 1 not vector in the size of 10 for the object size. The relations are inferred from the object's locations and sizes. The scene graph is processed by a graph convolution network, which gives us an environment-aware representation for each object. To support stochastic variability, we are concatenating to this output a normal distribution noise vector. The result is the input of two parallel networks. One creates a mask, and the other creates a bounding box. As you can see in the example, after creating the fixed-size mask and the bounding box, we are resizing the mask into the dimensions of the bounding box, and such creating the segmentation layout. Using a different network, we are also creating a small appearance vector for each object. In the training, it is done by using a ground truth crops of the objects. In inference time, we are expecting the user to give us those crops or traversing the network latent space. From all of these, we create a unified scene layout. The scene layout consists of the segmentation layout and the appearance vectors. The segmentation layout holds in each channel the segmentation mask of the relative class. As you can see at the beginning of this tensor. And the appearance vectors are the specific appearance of the different objects. These dual representations ensures that all the appearance data of each object comes solely from the appearance vector. Lastly, this scene layout is inserted into a residual network, which produces the desired image. As for the training, we are using 3 discriminators, among other losses, a mask discriminator, object discriminator, and an image discriminator. We'll talk briefly about each one of them. The image discriminator has 2 main roles. The usual one, it has to discriminate between real images and fake ones. And the other one is to identify a mismatch between the output image and the appearance vectors. I'll try to explain it using this the cat in the hat example, which, in case you wonder, it is a real image from the Coco dataset. In LReal, we are feeding the image discriminator with a real image, a real segmentation layout, and real crops. And we are expecting the discriminator to identify it as real. In the L alternative appearance, we are feeding the discriminator with the same real image, real segmentation layout, but with counterfactual crops. For each object, we are giving an image which has the same class, but with different appearance. This allows forcing the discriminator to consider the appearance vectors when outputting its result. As opposed to the image discriminator, which enforces convincing images, the object discriminator enforces that each object is identifiable. For this, we're taking crops of the objects from the real and fake images and require the discriminator to distinguish between them. And the mask discriminator is working in a similar way, only with masks and conditioned on the object's class. We'd like to talk about one of the most important losses in our model, which is the feature matching loss, introduced by Salomon et al. And this loss is returned 3 times in different variations in our model. A feature matching loss in our model is a weighted L1 loss between the activation layers of a neural network. We found that this loss drastically improves and stabilizes the image discriminator performance, and especially the mask discriminator, which otherwise suffer heavily from mode collapse and instability. The perceptual loss, which is a feature matching loss on a pre-trained VGG network, helps to stabilize all the different losses and improve the quality of the images, as can be seen in our ablation study. And now for the results. So our default resolution is 256 times 256 pixels. However, when comparing to the state of the art, we employ their resolutions of 64 squared pixel. For fair comparison, we also zeroing out our location vectors, and for each object, choosing a random appearance vector out of the latent space. And it means that our only input for these images is a scene graph. Except better looking results, we outscore all the different metrics, inception score, FID, and accuracy. Just a few seconds about accuracy. The accuracy test was made by training a classification neural network that when got a crop of an image, had to output its class. You can see that our score is getting closer to the real images score, and this is not a simple task. even with the real images, since crops may contain more than one object. To demonstrate the diversity of the model, we are presenting two experiments. The first one representing images which are based on the same scene graph, but with different sampled appearance vectors. On the left, you can see the ground truth image and the corresponding scene graph. On the right, presented images that were created based on the same scene graph when keeping the location attributes fixed at 0 and sampling different appearance archetypes from the latent space. In this second experiment, we are now keeping the appearance vector fixed and sampling from the location distribution. This sampling should be carefully done since we don't want to violate the object's relations that are defined in the scene graph. This diversity can be measured also numerically using the perceptual similarity metric. This metric presented by Tsang et al. Is trying to predict what is the perceptual similarity between two images. A higher score means that the generated images have a higher diversity. So we can see that even without using the appearance and location attributes, we are still outperforming Johnson et al. And when employing the full model, we obtain a leap in diversity. And in this last experiment, we are feeding the appearance network with 4 different reference images. All the other attributes are fixed. In the first example, we are changing the mountain appearance. You can notice the subtle reflection on the water, although the water appearance attribute is fixed. The second example, we are changing the bus appearance. And you can notice how the windows and structure of the bus are changing according to the appearance image. Our code is available on GitHub. Thank you very much for your attention.
We have time for a couple of questions, if any. Okay, I have one. Did you try to understand the interdependencies between the different subnetworks? I mean, are you able to quantify what is the contribution of each subnetwork on the generation?
Of separating?
Understanding the dependencies between the different subnetworks. I mean, you have different subnetworks that are used to generate the image. Did you study what is the contribution of every component, or is there a way of separating, understanding if there are errors, where do they come from? Is it the 3D model? Is it the graph generation? Or how do we deal with cases where we have something that is generated that does not appear visually correct? How you backtrack the information to improve your networks, the different subnetworks that you're training?
Okay. So we did an ablation study, which gives us numeric results about what is the contribution of each part of this model. The ablation study is in the paper. And except that, we did some tests to choose the best model. So we did some changes in the graph convolution model and in each part, and then we came up with this model.
Okay, so there's a question there. Go ahead.
Hi, this is a great work. I love it. I was wondering if you tried to work with relationships that were more than just spatial. So things like holding a cup or something. So semantic relationships.
Yeah, okay. So actually this model really can benefit from these relations. The problem that we had we have used, which has segmentation masks that we need in order to train the discriminator. So we use the Cocker dataset, and it doesn't offer these relations. For future work, I think it will be beneficial to find some new dataset, or maybe make some new one. We have some methods to create those segmentation masks on different datasets, and then do this test. I guess it will improve a lot this model.
Thank you.
We have time for one more question. Okay, I will ask a second question. Your graph actually is using any higher order dependencies, or are we only looking on pairwise dependencies? In the graph, you are modeling the dependencies. Is it a pairwise graph, or it also involves higher order?
So it's so the graph convolution it's done like 5 times. It's looking only in the neighbors. Like each node looks in the neighbors, but since there are cycles on the graph, and since there's only 8 objects, we expect it that theoretically each object can identify and know all of the neighbors around
Okay,
him.
but in the structure of the graph is a pairwise graph.
Right.
Okay. Last question, if there is any question. Okay, let's thank the speaker and congratulate him again.
Okay, now let's welcome the third presentation. It's best student paper. It's PLMP. It's point line minimal problems in complete multi-view visibility by Timothy Duff, Kathlén, Kohn, Anton, Leykin, and Tomas Pajdla. Let's welcome the speaker.
Okay, hi, I'm Tim. Today I'm going to tell you about a theoretical result. This is joint work with Kathlén, Kohn, Anton, Leykin, and Tomas Pajdla. Kathlén, Anton, and I are mathematicians who do algebraic geometry, and Tomas is our resident expert on computer vision. Now, the result is a complete list of minimal problems for reconstructing point line configurations in space. And my goal is to explain in very simple terms what exactly that means. So one of the grand challenges in computer vision that motivates our work is reconstructing a 3D world from many images. This has many applications. For instance, in 3D mapping from images taken by drones, in autonomous driving to localize and navigate cars in a 3D world, in the movie industry to reconstruct 3D background, for tracking moving cameras, and for combining real and virtual worlds together. Our main task boils down to reconstructing cameras and 3D entities, such as points and lines, from some corresponding 2D features. We assume calibrated perspective cameras. This means we have a pinhole camera with known focal length and an orthogonal coordinate system. So in this setting of calibrated cameras, we're looking for so-called minimal problems. Each minimal problem gives rise to a system of algebraic equations, whose number of real solutions will vary, but the number of complex solutions is almost always the same. In a typical 3D reconstruction pipeline, we have to solve lots of minimal problems in a ransack-style loop. Crucially, these problems depend on data which are noisy. Our definition of a minimal problem intends to capture the notion of a problem that remains feasible to solve even in the presence of noise. In other words, we want to be able to solve the problem for generic data. So now let's see some related non-minimal problems. So first, let's motivate the definition of a minimal problem in 3D with an extremely simple example in 2D. Suppose we want to compute a line between 2 points in the plane. The solution to this problem satisfies 2 linear polynomial equations in variables a, b, and c, and there's exactly one solution up to scale. This represents the unique line between the 2 points. And also, if we perturb the 2 points slightly, we'll still get a line between them. So in other words, we can say that solutions exist for generic data. Hence, in our language, this is a minimal problem with one solution. So now, let's see some related non-minimal problems. First of all, let's say we want to compute lines through 1 point. Well, then there are infinitely many solutions, because there simply aren't enough constraints for the problem to be minimal. And now for 3 or more points, we also don't get a minimal problem. The reason being that there are no lines that pass through all of the points, at least provided that the points are generic. Now, let's see a less trivial but still practical example of a minimal problem in computer vision. This is 5-point calibrated camera relative pose estimation. Here, 5-point correspondences in 2 calibrated views give exactly 20 relative poses, as long as the data are generic and we count solutions over the complex numbers. Thus, we say that this is a minimal problem with 20 solutions. Here's a non-minimal problem where we have only 4-point correspondences. By analogy with computing lines through 1 point, there just aren't enough constraints, and generic data give us infinitely many solutions. Finally, here we have another non-minimal problem, 6 points in 2 views. This time the problem is over-constrained, and for generic data, there are 0 solutions. And for the exact same reasons, we don't consider the popular 8-point problem to be minimal either. So all the preceding examples hopefully now motivate our main definition. We say that a problem is minimal if the number of solutions is finite and positive for generic image data. For 3D reconstruction problems, remember that solution means 3D entities and camera parameters. And so our definition includes the 5-point problem as a special case. So at this point, it's natural to ask, what other minimal problems are out there, and if we can somehow classify them all? Of course, we need to focus on simple 3D entities in order to get any understanding. So the class of entities we'll consider today will consist of points, lines, and some number of prescribed incidences among them. For instance, in these 2 images here, we might have used these window panes to match a point and 2 incident lines at that point. So that's our question. What are all minimal problems? And we answer this completely under one additional assumption that we call complete multi-view visibility. This simply means that each camera sees the same arrangement of points and lines, and that we're only trying to reconstruct that arrangement. So here's the statement of the result. We proved that there are exactly 30 minimal problems in complete multi-view visibility. This actually holds up to adding lines in 2 views, which don't constrain the cameras. So in 2 views, have as many common lines as you want. Otherwise, this is it. The other part of the result is that we compute the number of solutions over the complex numbers for generic data. This really gives us an intrinsic measure of each problem's difficulty. Of course, in applications, we're interested in one true solution only. Each minimal problem relaxes constraints imposed by the rest of the data, as well as real number and non-negativity constraints. So this is why we get other solutions. And hopefully it's clear that having fewer solutions is a desirable property that saves us post-processing time and leads to more efficient solvers. So in the next slide, I'll show you a table of the 30 minimal problems. For each problem, I'll show you the number of views, the configuration of points and lines in space, and the corresponding number of solutions. So here we have 2 views, a configuration of 5 generic points, and 20 is the number of solutions. So here are all the minimal problems. Maybe the first thing that you might notice is that there are no minimal problems for 7 or more cameras. Here, I've highlighted the 5-point problem that we've seen before. This next one I highlighted is a degenerate case of the 5-point problem, which actually reduces to another well-known problem, which is planar calibrated homography computation. Another 2 problems were previously discovered in a study of calibrated trifocal tensors by Joe Khalil. And last, I want to highlight some novel problems with few solutions that might be efficiently solved by current state-of-the-art methods. Also, notice that towards the top we have problems in 5 or 6 cameras, which have lots of solutions, and so we regard them as being very hard. Okay, so let me now explain how we did all this. To show that there are only 30 minimal problems, the proof has 2 main steps. First, we need to show that there are only 39 candidates, and this is a dimension counting argument. Second, we reduced the 39 candidates to 30 minimal problems using a Jacobian rank check. Now, to check minimality and to compute numbers of solutions, we use a suite of techniques that some have characterized as nonlinear algebra. The main tools here are basic algebraic geometry, symbolic methods such as Grubner bases, and numerical methods such as homotopy continuation and monodromy heuristics. We implemented our algebraic computations in a general computer algebra system called Michaeli 2. So to give you an idea of how we obtained the 39 candidates I just mentioned, I'll summarize the dimension counting technique. So in order to be a minimal problem, it's necessary that the degrees of freedom in 3D are equal to the number of degrees of freedom in 2D. So in 3D, each camera gives us 6 degrees of freedom. However, we lose 7 when we correct for inherent ambiguities in relative pose reconstruction. Each point in 3D counts for 3, a free line passing through none of the points counts for 4, an incident line passing through one of the points counts for 2. And now in 2D, in each view, a point counts for 2, a free line counts for 2, and an incident line counts for 1. So for the 5-point problem, cameras give us 2 times 6 minus 7, plus 3 for each of the 5 points in 3D, for a total of 20 degrees of freedom in 3D. And in 2D, for each of the 2 views, we get 5 times 2 degrees of freedom, also yielding a total of 20. So this passes our first test for being a minimal problem, which, as it should. Okay, counting dimensions is fairly easy, but it's not everything. The same dimension count gives us the following candidate problem. Here we want to reconstruct a point with 8 incident lines in 3 views. The number of solutions for this problem turns out to be infinite, even for generic data. So what we can see is that counting dimensions is actually not sufficient to prove minimality. Okay, so to identify which of the 39 candidate problems are minimal, we define something that we call a joint camera map. What it does is actually pretty intuitive. Its domain is a 3D space of points, lines, and cameras, and it maps into a space of 2D images, which we should also think of as a parameter space or a space of problems. The image of this map consists of problems which have solutions. And for the problem to be minimal, this means that the image of this map has the same dimension as the entire 2D space it maps into. So for each candidate problem, we just have to compute the Jacobian of this map at a fabricated generic point in the 3D space. And the problem is minimal if and only if this Jacobian has full rank. This is essentially just the implicit function theorem. So as we said before, minimal problems give us polynomial equations. So for instance, if we have a correspondence of 3 lines and 3 views, like we've shown, we know that pulling back each line along the respective camera map gives us a plane in the world. Now, we require that these planes intersect non-trivially, and this can be expressed as a determinantal constraint. Now, to compute the number of solutions, all we have to do is pick a random problem instance and solve it. So one way to solve such a polynomial system is to use symbolic computation methods, such as Grubner bases. So Grubner bases are a standard technique in polynomial system solving. And from a Grubner basis, we can easily determine the number of solutions for any of these minimal problems just by counting what are called standard monomials. Grubner bases and other algebraic techniques have been very successful in attacking minimal problems like the 5-point problem. They typically shine when the number of solutions is not too large, say less than 100. Now, we succeeded in finding solutions and the number of solutions for problems with 2 and 3 cameras using Grubner bases. Most of these trifocal problems had solution counts in the 100s, it turns out. Now, these computations can be more intensive as the number of variables, meaning the number of cameras, grows. And we couldn't successfully compute Grubner bases for any of the problems with 4 or more cameras using standard hardware. This is what prompted us to look at numerical methods. Homotopy continuation. So this is the numerical workhorse in our computations. The basic principle is to deform a generic problem instance A, whose solutions we somehow already know, into a problem instance B, whose solutions we want to know. So typically there's going to be involved some offline stage for solving instance A. And once that's done, solving B can be much faster based on this knowledge we have of A. Now, to compute the numbers of solutions numerically, we use a particular kind of offline homotopy solver. And this is based on the idea of monodromy. The starting point for understanding this is that it's very easy to fabricate generic 3D data and then take what we call the joint image. And this gives us a generic problem instance A with one solution that we know. So in this graphic, we see A downstairs in our space of problems. Now, we do homotopy continuation along random paths in our space of problems, eventually circling back to the fabricated instance A. This gives us a random monodromy loop in the parameter space. And the loop induces a permutation of the solutions of A. So we see the solutions lying above problem instance A in the 3D figure. Typically, when we do this, we discover a new solution, and this allows us to develop heuristics for finding many solutions. Now, the basic mathematical fact that makes this work is that actually all solutions for a generic problem instance can be discovered by these monodromy loops. Moreover, we find in practice that only a small number of loops are needed to reliably recover all solutions. This gives us an efficient offline solver that scales really well in the number of solutions, even the ones that have tens of thousands of solutions. Okay, so to conclude, there are exactly 30 point line minimal problems for calibrated camera relative pose and complete multi-view visibility. And for each of these minimal problems, we now know its difficulty as measured by the typical number of solutions. So if you want to hear more about this result or the methods of this nonlinear algebra that we used, well, ask me a question now, or please come talk to me at our poster this afternoon. Thanks very much.
We have time for a couple of questions. Go ahead.
Yeah, that's very good presentation. I'm just curious if you consider, in the book I wrote about 2004, we characterized almost all the configuration of multi-view of points, lines, and planes as well, that satisfies all this uniform rank condition, and that's for n views and so on. In your minimal problem, do you also consider that points in 3D can also lie on combination of planes? Because that also happens very, very often, right? So, because your title says complete minimal problems, have you considered that situation as well?
Yeah, so I mean, we do make an assumption that features are in general position. However, we do, as you also saw, recover this case of the planar homography problem. So we are able to recover some problems where without forcing this planarity constraint explicitly. However, it's not treated in our setup.
Yeah, so that's what I'm trying to say. That turns out it doesn't matter you have point lines, planes. They're all unified in the same class of constraints. You can characterize in the same rank conditions.
I see. Yeah, I guess maybe that's to be expected given the fact that we got this one. But
so, okay.
Yeah,
thanks.
interesting. Thanks.
Time for a second short question. Okay.
Actually, I have one question. Can you actually extend your model to uncalibrated cases?
That's a good question. I mean, yeah, so there are other camera models out there. It's not a question that we've really touched. But I expect that this program is probably extendable, though I don't know exactly how it's going to work out. I mean, it's a bit of a surprise that there are only finitely many in this case.
Thank you.
Okay, let's thank the speaker again.
Okay, so it's time to celebrate the last presentation. It's Marr Prize winning paper. It's SinGAN, learning a generative model from a single natural image by Tamar, Rott, Shaham, Tali, Dekel, and Tamar, Michaeli. Let's welcome the speaker.
Thank you. So my name is Tamar Shaham, and I'll present the work SinGAN, learning a generative model from a single natural image, which was done jointly with Tali Dekel from Google Research and my advisor, Tomas Michaeli from the Technion. So in recent years, unconditional GANs have shown remarkable progress. However, learning to generate high quality and complex scenes requires very large data sets. But what if we have only a single image? We introduced SinGAN, a powerful generative model that can be learned just from a single natural image. Given only a single training image, SinGAN is able to generate high quality, diverse samples that carry the same visual content as the image. SinGAN is completely unconditional. It maps random noise into realistic image samples and does not require any object class label or external data. This allows us to deal with general natural scenes. Once trained, SinGAN can produce high-quality, diverse image samples of arbitrary dimensions, which semantically resemble the training image, yet contains new object configuration and structures. So here, for example, you can see a new canopy layout and a new composition of birds. Training again on a single image example has been previously explored only in the context of textures, for the task of texture expansion and texture generation. However, these methods are not designed to deal with real images, with complex and non-repetitive global structures, as you can see in this example. In contrast, SinGAN is able to deal with general natural scenes. Shocher et al. Were the first to propose a single image GAN for natural images. Their work will be presented on the Thursday morning oral session. However, their method only solved the specific task of image retargeting, whereas our framework suits many different image manipulation tasks. For example, super resolution, harmonizing an object into an image, editing an image, transferring a paint into a realistic image, and producing a short video clips from just a single image. We solve all these tasks with the same unified approach and without any additional information or further training. And again, with only a single training example. So how does it work? The key idea is to generate a fake image whose statistic of patches is the same as that as the real image across multiple scales. To achieve this, we start by learning to generate the coarsest scale of the image. This is done adversarially with a patch discriminator, which attempts to classify each of the image patches as real or fake. Other than the adversarial loss, we also have a reconstruction loss, which requires that there is a specific input noise that will generate the real image of that scale. And actually, this way, we include the real image in our latent space. Once training is complete, we keep this generator fixed and move to learn to generate the next level. This only requires learning to add fine details on top of the upsample version of the generated images from the previous scale. Again, we use a patch discriminator trained on that specific scale, and we optimize the same loss function. We repeat this process up to the finest image scale. All the generators and discriminators have the same lightweight architecture with a receptive field of 11 by 11. Therefore, they effectively capture structure of different sizes within the image. Since our architecture is fully convolutional, at test time, we can generate images of arbitrary sizes and aspect ratios by simply changing the dimension of the noise map that we are injecting. We can train a SinGAN model with a different number of scales. A model with a small number of levels only captures textures. But as the number of levels increases, SinGAN manages to capture larger structures as well as the global arrangement of objects within the scene. In practice, we always adjust the number of levels such that the effective receptive field at the coarsest scale is about 40% of the short axis of the image. This is what actually allows SinGAN to generate both large structures and fine details. Note that the training image can be of any size. To quantify the realism of our generated images, we performed user studies through Amazon MTurk. Images were randomly chosen from the places dataset, and we trained a SinGAN model for each of them and produced random samples. We had two types of tests. A pair test, following the protocol of Zhang et al., where a real image was shown alongside our fake version of it, and the user had to pick the fake. And an unpaired test, where a single image was shown to the user, which had to determine whether it's real or fake. The confusion rates in both cases were relatively high, with the unpaired test nearing 50%, which is the ultimate score in this task. This is while the fake images are significantly deviate from the corresponding real images, and you can see our paper for more details regarding that. The multi-scale architecture also allows to control the diversity of the generated samples at test time. When starting the generation from the coarser scale, we get highly varied samples. However, we can start the generation from a finer scale and inject a downsampled version of the training image as an input. This way, we can modify only finer image features. This is useful when the image contains one large silent object and we want to keep its global structure intact. Here, for example, when starting the generation from the coarser scale, we get non-realistic zebra samples. However, when starting the generation from the second coarser scale, only the zebra stripes get modified. SinGAN's ability to preserve the global structure of the injected image and to modify only fine details has many applications. Specifically, note what happens if instead of the downsampled training image, we will inject a different image to one of the trained model. SinGAN can only generate images with the same patch distribution of the real image. Therefore, attributes from the training image are transferred to the injected image, producing an image-to-image translation effect, but with only a single example. Note that this task is challenging even for models like CycleGAN, which were trained on thousands of examples. This property can be used for many image manipulation tasks. For example, we can train SinGAN on this image and then inject this pane to the second coarser scale. The result is a realistic image that contains the global structure of the paint, but the appearance of the training image. Here's another example for transferring a clip art into a realistic image. Here, simple color spots are transferred into cows. For comparison, here's what happens when using single image style transfer method. In contrast to SinGAN, these do not transfer any semantic content. Similarly, we can input an edited version of the training image. Here we simply copy and paste a few patches. SinGAN translates this edit into a coherent and photorealistic image. Photoshop's content-aware move is not able to generate realistic result with this challenging edit. Here's another example for image editing. Here, SinGAN modified more global structures to match the edit, whereas content-aware move performs more local changes. We can also harmonize an object into the training image. SinGAN tailors the pasted object texture to match the background. This blending effect is different than other approaches like deep painterly harmonization, which impose color matching with the background. The chosen injection scale has a strong influence on the result. The coarser the scale we inject the input image to, the larger the structures that get modified. When the input is injected to a fine scales, only fine texture get modified and the global structure remains fixed. This is true for all applications. So the user can simply choose the desired effect. This harmonization approach works for paintings, and also for real photos. SinGAN can be also used for super resolution. Inherently, each of SinGAN scales add content on top of the upsample generated images from the previous scale. So imagine we could train the SinGAN model on this low resolution image and then continue to upsample it using additional scales. Unfortunately, we do not have these generators because they correspond to image scales that are larger than the training image we have. However, since the statistic of patches within natural images tend to be similar across scale, we can simply assume that all the missing generators are equal to the last generator we have. Now, inputting the low resolution image to this extended pyramid leads to a super resolution effect. As opposed to other methods trained only on a single image, like deep image prior and zero-shot super resolution, SinGAN produces much sharper reconstructions. Surprisingly, SinGAN performs similarly to SRGAN, although SRGAN was exposed to more than 300,000 images during training. This is seen in a quantitative evaluation on the Berkeley segmentation dataset. In terms of perceptual quality, quantified here by the Nike image quality measure, we are only slightly inferior to SRGAN. Here, lower is better, and also significantly better than other methods that target PSNR. In terms of RMSE, we are on par with SRGAN. One of the interesting properties of our super resolution scheme is that instead of super resolving a low resolution image, we can also super resolve random samples. This enables us to generate high definition images, which is often considered a real challenge with unconditional GANs. Here, for example, we generate 4 megapixel samples. Another application is animation from a single image. Here we travel through SinGAN's latent space to produce smoothly varying video clips. We found that for many types of images, the most realistic effect is achieved by a Gaussian random walk with momentum in the latent space. So the effect is that these still images can be brought to life. Here as well, we can control the animation effect, both by changing the random walk parameters and by choosing SinGAN scale participating in it. So for example, we can animate a light wind, or a strong one. To conclude, we introduced SinGAN, a powerful generative model trained only from a single natural image. We showed how SinGAN can be used for generating realistic image samples, and also for a long line of image manipulation tasks. Our code is available, so you're welcome to check it out. And in this opportunity, I would like to thank the award committee and to invite you all to our presentation and poster session on the Thursday morning oral session. Thank you.
We have time for several questions. Okay, I have one question. How do you think that this method will scale to non-natural images? Like, for example, medical or digital pathology?
I think it has many potential applications. It could be trained on other types of images, like medical images, for example. It may need to have some adjustment, but yeah, it has the potential to be beneficial for this.
And how it will scale if we go from 2 dimensions to 3 dimensions?
So all the upsampling process, for example, should be appropriate to 3D signals, for example. You need to do all the architecture and the upsampling process appropriately.
Okay. There's one question. Go ahead. Go ahead.
Go ahead. Yep. Oh, hi.
Hi.
So you showed one picture with a bunch of cows in a pasture, and then you showed a comparison to some other work. Was the reason yours looked better is that you were escaping some kind of many-to-one problem that you would have if you trained with multiple images?
So I think the interesting property is here that you can actually capture the semantic content of the image because you train it across multiple scales. And at specific scale, those cows look like a simple spots. And therefore, the model knows that in this specific scale, if it sees spots, you need to transfer them into cows, whereas other methods cannot do that.
Okay, there is another question there.
Hi. It looks like once SinGAN is trained, it is kind of limited to the single training image. Have you considered the way of training it with multiple images?
This is actually an interesting question. We didn't try that, but I'm pretty sure you can kind of combine both this internal training with some external methods. This could be interesting, yeah.
Thank you.
And we have time for a last question, if there's a last question. Okay, let's thank all the speakers of the session. Okay. And our committee as well for actually making the job behind making this session happening, and enjoy the conference.
So I do have one quick announcement. Posters will be presented in 2 different places. Posters number 1 to 40 will be presented here, D1 swing, so-called, and also posters numbers from 41 to 170 will be presented in Hall B. So please aware those 2 different places. Thank you.